Next in this track, we've got a panel, Emerging Computing Technologies in Academia and Industry. What is the next big thing in cloud computing? What are the disruptive technologies that are just around the corner? How can industry and academia work closer and better together? To answer these big questions, we brought together some big minds from Microsoft and academia. These are the people who are working at the frontiers of the cloud, cloud intelligence and its applications. Our distinguished panel includes Yuan Zhao, a professor at UCSD, Dave Maltz from the Azure core team who runs Azure Networking, John Sheenan from Azure Edge and Platform, and Jim Clewine from Office 365. And our host for this next session will be Thomas Karaginis, a principal researcher from the Cloud Systems Future team here in Cambridge. So let's go and hear what they've got in store for us.
Welcome to the fifth session of the Future of the Cloud track, which is a panel discussion. My name is Thomas Karagianis, and I'm a principal researcher at the Cloud System Futures Group at Microsoft Research Cambridge, UK. I will be moderating this panel session, which for the next 45 minutes aims at discussing emerging cloud computing technologies with disruptive potential and how to align efforts across academia and industry. I would like to believe that we have the most excellent panel composition for this discussion, so let me quickly introduce the panelists. Wang Zhu is a professor in mobile computing at University of California, San Diego since 2009. Her area of expertise includes cloud reliability, data center management, and cloud security. She obtained her master's and PhD from Princeton University, and she is an ACM Fellow, an IEEE Fellow, a Sloan Research Fellow, and the winner of the prestigious ACM Mark Weiser Award in 2015. Yuan, actually, in parallel to her academic career, she has also co-founded 3 companies, one of which was acquired by VMware. So besides being a leading professor, Yuan has thus a lot of experience interacting with the broader industry. John Sheehan is a corporate vice president, distinguished engineer in the cloud and AI business at Microsoft. He runs the Health and Standards team, which owns the health infrastructure and standard cloud architecture systems for Microsoft. Previously, he was responsible for the architecture of the Azure IoT platform and services. Outside Microsoft, John is also very active in various ways in encouraging women to pursue careers in STEM, and he volunteers time with Ignite Worldwide, an organization dedicated to achieving gender equity in STEM. Dave Maltz is the engineering leader for the Azure networking team, responsible for developing, deploying, and operating the software and network devices that connect Microsoft's largest services, including the Azure Public Cloud and Microsoft 365. Dave is essentially responsible for the team that designs the cloud-scale networks and data centers that provide petabits of connectivity with high reliability, all the way from the optical systems and up. Dave has also been a member of Microsoft Research in the past with many publications, awards, conference keynotes, so he's very familiar also with academic research. And last but definitely not least, Jim Clewine is a Microsoft Technical Fellow and currently leads the team responsible for the cloud services supporting Microsoft Teams, Azure Communication Services, and Skype. He has worked on Office 365 cloud services since the very beginning and was actually responsible for many of the initial designs, architecture, and technical approaches that moved Office servers essentially to one of the world's premier hyperscale cloud services. Thank you all for joining the panel again and for participating. Now, before going into our main discussion, actually I would like to have a quick warm-up round, and I'm going to ask from you just 2 words. So these words would be, what are the 2 words that come to your mind? 1 word for describing the biggest challenge of a future cloud, and 1 word would be for the biggest opportunity for the future cloud. And we can go in the order of presentation that I just used. Maybe we can go from Yuan to John to Dave and Jim. So Yuan, over to you. 2 words.
So the first word in terms of challenge is the complexity. So do I need to explain, or I just give you 2 words?
Just give me 2 words. Yes, we can go over them on the next.
So the challenge is the complexity, and then the second word in terms of opportunity is really is data.
Okay, John.
I think my 2 words would be scale and efficiency.
Darn, John, you stole mine, but I'm going to double down. My 2 words are scale and scale.
Yuan took one of mine. I think the biggest challenge is complexity, and the biggest opportunity is enabling.
Wow. Okay. So there does seem to be a lot of both agreement and a lot of diversity in the words used. So let's keep these words in the back of our mind, and let's move on to the main discussion. So I would like to start in reverse order now and go through the cloud stack from the bottom up, starting with the infrastructure. So perhaps this question is mostly for Dave and Jim, but John and Johan, feel free to jump in. So we have heard talks in the earlier session of the future of the cloud track, with research exploring very different approaches as to how we do compute, networking, and storage. For example, we have heard talks exploring optical computing, or storing data in glass with Project Silica, or innovating across the whole networking cloud stack. And in my mind, these types of innovations and these types of research is trying to address the fact that traditional technologies such as CMOS have stopped scaling. And I believe this is well accepted now. Now, my question to you is this the right time for these types of technologies to feature in the data center? And if so, what does this path look like? How do we take these disruptive technologies and make them a reality? Or is it still too soon for them? So maybe we can start with Jim.
So thank you, Thomas. I think that it is a well-established fact at this point that Dennard scaling and Moore's law, if not all the way dead, are certainly getting closer and closer to it every day. Dennard scaling is long dust, and Moore's law is more debatable. The emerging technologies, I think, are things that we have to start to explore and we have to start to incorporate into data centers if we're going to continue to do things like scale, one of the words that we heard for both challenges and opportunities from both of us. And if we're going to try to allow us to make the solutions more simple, we have to have changes in the underlying technology platforms, the underlying foundations of computing and foundations of data centers, to enable the really complex parts of the data centers, which is the software, to continue to be as simple as we can make it. So the right time to innovate in these new technologies is always. We've always got to be on the cutting edge of doing this if we're going to continue to scale, if we're going to continue to offer the ability to be simple. You know, while Moore's law is dying and Dennard scaling is dust, that doesn't mean, even at the lowest level, at the silicon level, that there's not room for innovation. You know, I'm cautiously hopeful a lot of the work that's going on the science side for graphene will play out, and we'll have a whole new class of computing devices coming out. I'm very excited by improvements in optical and the work like silica and other optical work like it, because no matter how much we would like to, we still haven't kicked Einstein's butt. That speed of light is still as close as we can get to fast, and anything that gets us closer to the speed of light is a good thing. I love the innovation coming out of AMD on chiplet technology. So even if Moore's law is dust, it doesn't stop us from continuing to scale the number of cores on processors and to do it in an economical way because of their chiplet architecture. So I think there are tons of ways in which there's still innovation at those lower levels of the stack. And even moving one click stop higher from the silicon level into the computer architecture level, if we look at it, a lot of the fundamentals of our computer architectures have remained stalled for, 20 years maybe. I mean, a rack of servers is still largely, well, the same architecture that a server was 20 years ago, where you've got the processors and the buses and the DRAM all in a package solution tightly bound together. We haven't really revised the basic computer architecture to reflect the fact that we're not dealing with pizza boxes stuck in a rack. We need to realize we're building and operating hyperscale services and look at innovation at the computer architecture level to really drive some of that forward. Question some of the basic presumptions that have kept the computer architecture really stale for 20 years. One of the things that I love about all of the work that I do with research and with academia around the world is that research and academia explore the realm of what's possible, less hindered by what currently exists. They have a tendency to think outside of the box, where within straight line development and straight line engineering, we are relentlessly incremental. And sometimes you have to stop being incremental, and you have to allow the giant leaps that you can only get by crazy outside the box, innovative, what happens if we change a fundamental presumption, thinking that we tend to get more from research and academia. So I'm very, very bullish on the future for the bottom lines of the stack. And the thing that would make me even more bullish is if we had more and more researchers who were looking at those bottom layers of the stack, at the stodgy old boring systems level of the stack, and saying, how can we really innovate there? Anytime something gets to be really static, and anytime something becomes accepted as the way things are done, that's the time we most need the crazy thinking and the research and the innovation.
That's actually a great path to maybe ask David. We can kind of innovate and we can think outside the box. The question is, how do we bring this into a, as people mentioned, like a complex system which is of a huge scale. So what would be the best way to do that? What is the path to achieve this?
Okay, great. So, Jim, I completely agree with a lot of the things that you were saying there. Maybe just put a little bit of a networking twist onto that. I said the challenge is scale and the opportunity is scale, because the cloud and the future of computing is really about limitless computation, right? How can we take all these resources and make them look to a user as if they're one fungible, infinitely dividable, infinitely expandable set of resources that they can apply to whatever project or problem they're trying to solve. To start with the first premise though, never bet against the device physicists. I mean, those folks have come up with innovation after innovation. So yeah, all of us should keep our computer architecture hat on and look to see what's happening at the various lowest levels of innovation. Some really radical things are coming there in multiple fields that could then change what we as computer scientists have to do pretty dramatically. In terms of solving this problem, yeah, let's take it for granted that the simple scaling that we've been getting from Moore's law is over. What does that mean is going to happen? Well, great. We are going to replicate more units of computation, and that's how we're going to get more scale, which essentially means all those problems of parallel computing that we thought about a lot several decades ago and then have been able to largely put down and ignore for some period of time are coming back at us. So I actually start thinking about this problem essentially at the programming model level. The kinds of programming models that we've been using are not very amenable to the type of infrastructure that they're likely to be running on in the future. And that's really where thinking about storage in a different way, thinking about serverless or stateless computing, things like Azure Functions, those are very powerful programming models that make it relatively easy for humans with our demonstrated limited ability to think about parallelism to actually write code and programs that are going to work. As we then start to take that, what we want to expose to the programmers and the users of our systems down to the next level, Like Jim was saying, computer architecture becomes really important, but I want to call it a couple things in particular. The coherence architectures, like what is that memory hierarchy, and to what extent can we simplify the programming model for the language designers as well as for the programmers by maintaining coherence at the architectural level? That's really hard because as the scale goes up and the number of things we're trying to maintain coherence over increases, it's easy to lose a lot of performance. This is fundamentally a systems and networking problem. Why do I say networking? Well, okay, I'm a networking person, but imagine what happens, right? So essentially, we're going to get more scale in our computation by adding more endpoints into our data centers or into that sort of computing infrastructure they're running on top of. All right, so interconnect becomes super important then, right? And that interconnect is the network. I think we're going to have lots of different kinds of interconnect. The speed of light is the ultimate speed limit out there, but there's also factors of like how much power it takes to drive information from one chip package to another, from one box of chip packages to another box of chip packages. Typically, the further you go, the longer it takes, but also the more energy it takes. And power consumption and the ability to remove heat from data centers and the components of the data centers is really becoming a limiting function, a limiting factor on how big we can build these things. And so for those reasons, we're probably going to end up in a world where your data center, that set of fungible resources, is going to look like a very non-uniform memory architecture. And again, the programming languages folks are going to have to figure out how to expose that to users. And we as the systems and computer architecture are going to have to find ways to try and simplify it as much as possible. What that also means is that the networking space, lots of room for innovation because we are going to be managing different kinds of interconnect. But we want those different interconnects to work together seamlessly. That may be data buses specific for memory, different ways of managing storage, both local and remote, as well as then the ability to get data between lots and lots of specialized coprocessors. GPUs, TPUs, DPUs, IPUs, star PU is the name of the game in systems. And each of those things has different requirements for how they need information to transfer between them and what assumptions they want to make about the interconnects underneath them. So there's this really interesting interplay between the people designing those coprocessors and essentially the transport libraries and the interconnect networks that we're going to build to move data around inside the clouds of the future. And then I guess the final point I want to make on this is, we can't forget that this is a physically embodied thing. And so work in optics, super important, again, can reduce the energy per bit it takes to transfer data, but also gives us a way to then physically cable these sort of monsters that we're creating. These ultimately have to be reduced into three-dimensional spaces where cables can be run in ways that we can actually build a facility that can be scaled out, that can be maintained, that can grow over time. People often like to think about, oh, the supercomputers of the days of yours. Those were typically built all at one time as a special purpose computer. The world of the data center and the cloud is continual deployment. And what that means is I always wanted to be deploying the most efficient, newest technology. That means if I look in our data centers today, I still have some stuff running at 10 gigabits per second, servers at 10 gig networks that haven't been decommissioned yet. I've got stuff at 40 gigs, 50 gigs, 100 gigs. I've got stuff at 200 gigs and 400 gigs coming. And so there's going to be this heterogeneous mix of the physical infrastructure. But again, our goal is to enable true multi-tenancy, where we can take many different workloads running on top of this heterogeneous infrastructure while still giving every user the view that they have a homogeneous cloud that is perfectly isolated to them, so that there's, what one user is doing doesn't impact anything another user is doing. And that creates a whole bunch of interesting systems challenges as well, from everything we saw with some of the cache leakage behaviors, Meltdown Inspector, to simple performance isolation. Anytime that there is a place where two different workloads come together, there's a potential bottleneck where the behavior of one cloud user could impact the performance seen by another. We have to solve all those problems as well.
Actually, they are going to pick in one line that you use, that humans have this limited ability in understanding these sort of complex systems. And I'm going to kind of try to move up the stack and ask you and why What do you believe is the role of AI operations in sort of these complex cloud scale systems? Are we going to be relying on AI completely to run the systems, or are we going to have humans in the loop? And how does this interaction look like? What are the challenges for AI to ensure like that we have a truly ubiquitous, always-on cloud?
Actually, as I mentioned, there's all this heterogeneous and also constantly evolving, right, with all the new devices. It's really beyond the human's capability to kind of manage. This actually, I found that this problem in my, when I did my previous startup, it was really the cloud, the backend management infrastructure. There is already fairly complex, where all this new emerging technology, and sometimes they really use a completely different kind of a set of standard or API. So manage them actually, especially like do troubleshooting or like a kind of or security forensics is actually really kind of challenge. I think there's a whole lot of effort in this on the infrastructure side. So the current startup actually is more, I'm doing it on the cloud applications. So I realized that the things is much, much worse because of the human. Actually, like these days, since I'm also from academia, like application, like developers, the CS computer science students, they are moving up, right? So right now I'm teaching OS classes. At the UCSD, OS is no longer required for students. So in this case, what does it mean, right? So then that means like we're going to produce a lot of developers. They don't understand the backend, like all this basic low-level stuff. So now you imagine they're going to join some company, do e-commerce, even though they're not like a part of like a big, like a Microsoft or Amazon, those are like a cloud service provider, but they have to manage the cloud applications. And which also use a lot of like database server, like kind of also like for example, object store, many kind of different boxes. That they also use a third-party service providers, right? So it's all like a kind of intertwined together. And I found actually even sometimes a master level, like a developer with a master degree, they really don't know how these boxes operate with each other. And when something goes down, it takes, quite a bit of long time to find one of the third-party library had some issues because, because you need actually to communicate across the cloud to the service provider, right? Some kind of application level service provider, for example, the one providing your map, right? So I'm actually quite really worried. So, but I think the trend is going to go this way because students want to learn like data science, AI, something more high level, right? So the challenge, I think, is then the like management naturally going to go more towards automation, and the AI is a way of automating things. So that's actually the kind of way. And maybe kind of for the human part, I think it's really another part actually I have been very passionate is this human interface. Because like our mobile phone, we worry about the UI, UX, but in the data center management or some kind of management thing, I think UI, human interface interaction is not a big kind of like a kind of requirement. So as a result, it's actually many times the way we to manage things is to read a lot of logs, right? Kind of what's going on to be able to understand. So I think it's like on one hand we should use automate as much as possible using any kind of intelligent like AI algorithm or some automation. And on the other hand, for things we cannot fully automate, we really need to emphasize the kind of human interface. Is there any way we can visualize in a way for them to be able to easily see where is the problem? And so I think that is a kind of the part. I think I'm actually particularly worried about not the, like the infrastructure level. I'm more worried about the application level right now. I don't realize, how unprepared that those application developers are.
I see.
Can I jump in there, Thomas, with just one comment? Because I love what you said there about the people, more people learning systems and learning operating systems, because I think the real differentiated skill set for students of the future is going to be people who understand and can reason across the entire stack. because of the complexity we started talking about, and because of a lot of the things you brought up. So, keep training as many of those OS students as you can.
So, John, since I think you are kind of the best position to talk about health and infrastructure. So, what are your thoughts given the picture that YY painted on how students sort of move up and sort of ignore everything below?
Yeah. So, I mean, as a longtime operating systems guy, it breaks my heart. Operating systems are really fun to learn about, and it's kind of unfortunate that it's not even a required course anymore. And I do think that is going to cause major challenges. I already see it now, with sort of new students coming into, into Microsoft, trying to debug very complex issues and sort of hitting a wall where they just don't understand how that level works. And those black boxes can be really dangerous at scale. But as far as operating our cloud, so I own the health and standards team, and part of my team is building the AI ops platform for us for operating our fleet. And when I look at the scale of telemetry we get right now, just from our clouds, we get now we're at over 500 petabytes a day. There is no way that humans can look at all that data and make any sense of it at all, right? We're way past using humans to operate at the scale of our cloud. And so, my team is constantly looking at what are the ways that we can take that data and, reason about it and figure out automatically things like something as simple as service health, right? If you think about just take one service that's running and just try to figure out, is it currently healthy? That's not even a binary thing, right? I mean, we've got millions of customers running on that one service, and some of them may be having a great day and a couple of them may be having a bad day. And being able to go through the data and figure out like what's going on. Another big one is introducing change to our fleet, right? So I don't know how many thousands of changes we push a day. Any one of them can cause customer pain and customer impact. Figuring that out and detecting it before it happens, when you're trying to sift through, over 500 petabytes of data, like the numbers are just mind boggling. And we know that we're growing, like we're constantly having to plan for 10x growth, right? So the challenges that we have today are a small piece of the challenges that we're going to have in the future, especially when you start thinking about how we're growing. As Dave was talking about, we take a unit of compute. I think of a unit of compute as like a data center. And we just keep stamping out more and more and more of them. And the rate at which we're stamping them out is going, up and up and up. And so that means, when we talk about complexity, we talk about operational complexity. And operational complexity is actually a product of the overall workload that you're running times the number of places that you're running it. Because if you actually look at these systems, they sort of look at each one independently because they have to for fault isolation reasons. And so, our operational complexity is just going up and up. And really, automation and AI is one of those technologies that, currently there's tons of promise with AI, but there's some stuff it's really good at, and that happens to be the things that we need it to be good at. So, in many ways in kind of the health space, we're fortunate that, there's so much investment going into AI right now. And then when I think about like the future of these data centers, yes, we're trying to scale and scale and scale, but I'm also starting to see a lot more specialization, right? Inside of our fleet, we're starting to use, all kinds of different cards that are specialized to handle a certain piece of the workload to free up the general compute for the customers. We're starting to see things like TPUs, where we can have specialized compute that says, yes, Moore's law is not scaling the way it used to, but that's okay because general compute isn't the only way to go. There's also specialized compute. We're looking at all of that as how are we going to deal with these, this ever increasing amount of telemetry and data that we're getting. Like we're going to have to go specialized to deal with it.
I see. Thank you for all these insights. I think I would like to spend the last 15 or so minutes of the session discussion on how industry and academia help each other on this sort of very difficult journey through complexity scale, as you mentioned. So, you, I think you're coming from academia, but you also have sort of experience interacting with industry. I guess academic research is not, as Jim mentioned, not bound by the restrictions and constraints of existing systems and existing clouds and how they run and so on. And they can offer very different perspective to new technologies. So in your experience, what is the best way to get some of these insights towards the industry and not just keep them in a corner in academia where we like them in conferences and so on, but they never made it to reality? So what are your thoughts on this one?
So I think one thing is like academia. Actually, the good thing is we typically faculty have a sabbatical, and also students they can do internship. Like for example, I have probably 3 PhD students who did an extended internship at Microsoft. Actually, with Azure, not with Microsoft Research. So I think like one student stayed there as a sort of intern for 1 year. I found actually sometimes like a 3-month of summer internship is not that effective because it takes them probably 2 or 3 months to even understand the system and how things work, where are the data. So I think sometimes this kind of way, if there is some kind of way to do extended internship, I think especially for PhD students, it's actually they love this opportunity. Also for the professor, they love this kind of collaboration because due to the constraints, because if we just purely collaborated this way, like the students cannot access the data, right? They're not the employee of the company. So for like many time in IP issues, it's better for the student to be hired as an intern, so the students can access the data, but the professor usually just advise the project, collaborate with the Microsoft, people from Microsoft together. I found that to be very effective because both of the PhD student and the faculty, they can do things a little bit extreme in terms of like, for example, David talked about the programming languages, right? So we actually completely propose a language. We're not worried that much about adoption, but we will be able to explore different kinds of languages. And then that maybe not be immediately used kind of right away, but it could be some in the future, near future, some elements of the languages could be put into like the kind of the business, actually the real world, right? So that's kind of one thing. Another part of a thing is like a professor actually can do sabbatical for sometime 1 year or even extended the time. I found that for me, because the benefit to do a startup actually really beneficial for my research, because if I don't go to the industry, I would never realize many of the problems. So for us, like especially maybe since we work on computer systems, I think we 100% stay at university, we're not going to know what a problem out there. So I found out have researchers from academia to go to industry, spend some time, they can take the problem back, and then they be able to, this way when they come up with some solution, still is relevant. You're not like completely off the chart in our own toy mind to think about the toy problems, right? So I think that is, this way is those kind of solutions are more easily applied back to industry. Like the second startup was actually you mentioned quite about VMware, was really we discovered. I was like in the toy now to do debugging, like find the bugs in source code, but then actually want to talk with industry. They say it's many times actually they say we have tons of bugs. I don't want you to tell me we have more bugs. So can you help us troubleshooting, diagnosis? And many times we cannot reproduce the problem. We can only look at the logs, right? That's how we be able to diagnose and analyze. And then is there any way you can help us intelligently analyze the logs? So that's actually I took the problem. Of course, we use something like AI, all kinds of techniques. Some is actually, so when we come back to build like the product, is some of the AI algorithm not accurate enough. We have to remove them, because once you apply to the industry, accuracy is super important. You cannot introduce so many false positives in troubleshooting. So I think that's, but then part of our actual solution works because it came from the industry. The problem started from the industry. So like a part of the things, we more exploratory cannot apply to a product right away, but a big part can actually become a product. So it's still right now used in data center to do this kind of like data center monitoring, like health monitoring, security forensics. Yeah, so I feel like these are kind of ways of collaboration. Definitely other people can jump in.
Yeah,
Go ahead, John.
I'll say, like, I've noticed in the last 5 years that this relationship between, like, at least Microsoft and universities is starting to change. In the space that I play in, we now directly talk to the professors and the students about the challenges that we're having and saying, hey, do you have anything that can help? And in some cases, they already have something. And then in other cases, they're like, oh, interesting problem. Often they're like, can you give me data? In a lot of cases, we can, because it's our data. It's about our servers, it's about our hardware. And so, yeah, so that relationship's really changing. Like, my team sponsors a partnership with Stanford that we participate in their System X program. And that's one way that we get access to the professors and the students to sort of start to collaborate at the level of not, hey, someday it would be great, but like, here's our current problem, and here's what's happening, and it's going to come in the next few years. What can we leverage to solve it? Because we can't wait. We can't wait 10 years for something to happen. Like, we need it now.
Right. Dave, I guess you also have experience in both camps, research and industry, and I guess more kind of product side role. So what are your thoughts on that one?
Well, yeah, I've personally gone back and forth between research and production land a couple of times. Like Yuan said, the human factor is very important. So doing internships, doing sabbaticals in industry is probably still the best way to really get deeply embedded in some of the challenges that are going on. And during those types of sort of visits, long-term visits to the production companies, we're typically able to include people and show them all of the data. Well, John said some data we can share because it's essentially about our systems. Job number one for us in the cloud is safeguarding the customer data that's been entrusted to us. We work very hard to make sure our employees and staff don't get anything that would give insights as to what our customers are doing on top of our cloud. And we're making big investments of confidential computing to sort of strengthen those guarantees even more and more. So I have had, I've been part of conversations where people have asked me, hey, can you give us this data? And I have to say no. Even networking data, which you might think is like, oh, it's just traffic utilization. But detailed information about traffic utilization can say quite a bit about what a customer is actually trying to do with that cloud infrastructure. So that's a challenge that we're just going to have to operate from. As has been mentioned, sort of consortiums or collaborations between industry and specific research groups, I think those have been very fruitful. One of the things I'm missing, though, is sort of places where people from multiple companies and multiple research groups can come together to work together. Microsoft does do a lot of work in the open source space. We started Sonic Software for Open Networking in the Cloud, which is an open source operating system for routers, precisely because it eliminates a lot of the intellectual property issues and concerns. Be nice to see if we can do some things like that in this cloud infrastructure space as well. Although we compete fiercely, Microsoft does with other cloud hosting companies, there are places where it seems like we face similar challenges, and collaboration, even among the cloud providers, is possible if there was this kind of neutral ground that we could all come to participate in and then collectively draw insights from. So those are some things I'd love to see happen. One final comment is that there have been a lot of statements of the fact, oh, it's impossible to do academic research on the cloud unless you have something to scale of the cloud. The cloud is all about scale. And there are certainly problems where that is true. However, some of the things we talked about today, like programming languages, like architecture, like even the details of how we get high quality of service and tune buffers and specific routers and switches, those are things that do not require complete access to your own cloud in order to run those experiments. So there's a lot that can be done not having a cloud. And then there's a lot that can be done running on top of the clouds that are already out there. And so, I think all the cloud providers have programs by which we can make VM hours and other compute resources available to academic researchers. Really encourage everyone to take advantage of those, because that essentially gives you access to largely the same infrastructure that we're building on top of as well. And so part of our job as cloud providers is to make the full power of these platforms available to everybody, and that includes academic researchers.
Jim, I saw you nodding a few times, so adding to that.
I mean, I think Dave gave us a great setup there with his final comment to bring us back to where we began, which is what's a lot of the opportunity in the cloud. And if you remember, my word for opportunity was enabling. And I picked enabling because the cloud really allows us to democratize access to the massive amounts of compute and the massive amounts of data that's necessary to do research, to do cutting edge innovation. And really creating consortiums, creating projects like YY and John were talking about, and then using the cloud to enable them to work with the data, to work with the scale is a great way to do this. It doesn't have to be consortiums. It can be things like what my current team does, which is challenges. We have challenges that we issue where we provide data and objective metrics and say who can come up with the best new AI-powered video codecs. And we're looking to things like our Teams product and saying, hey, we could really use that to reduce things like network bandwidth and to allow networks to scale, as Dave was talking about. And we have a challenge and say, hey, create a group and compete in the challenge. See if you can beat the objective metrics on the data. Doing the same thing with noise cancellation and eliminating background noise. There's so many different ways that we can collaborate. In my own experience, everything YY said are the best ways to do it, which is form relationships. Because in the end, clouds are about software and services are about people. They're about the relationships between people. And having great relationships between academia, between research, between product and engineering groups is the way we're going to drive innovation here.
Thank you, Jim. I believe we're getting close to kind of the 45 minutes. So thank you all for the very interesting discussion. Any last words that you would like to add from anybody on the discussions?
I'll just say, I mean, the cloud remains such an interesting and challenging space. I'm sure there's a pendulum swing. The pendulum is still swinging towards cloud and making that work. 10 years from now, it'll probably be swinging back towards dust computing or something like that. But this, I think there's so much exciting stuff happen as the world continues to innovate and unleash the power of clouds and the size of the problems that can be solved using these massive pooled resources.
Yeah, and I'll definitely make a plug for operating systems. As I think Jim mentioned earlier, the places where you sort of feel like, oh, that's done, we're good there, let's move on. Those are often the places where there's the most opportunity. And I can tell you, my team also tries to keep the, like the 1.5 billion Windows PCs around the world healthy. We're nowhere near done with innovation in operating systems. So I really hope that more research continues there. And more of the students that come out of universities come out with that skill set, because it's vitally important to understand that if you're going to try to troubleshoot anything.
Yeah, total +1 to both of those, especially John's comment that we're far from done here. I would like to think that we've barely begun, not that we're done in any of this.
Yeah. So follow like all you guys' comments. I think I'm also hoping, like industry experts like you can come to academia to give a talk, share the challenges, exciting things happening especially on the back end of the cloud infrastructure, because I really wanted, like you guys help excited the students. Besides the fancy, upper level things, there's a really, really cool things on the cloud infrastructure side, on the cloud side. So I think this way really help, like we can produce, we can attract more students to have those kind of skill sets, willing to, learn those kind of skill sets, at universities, and be able to, prep them for the workforce.
Sign me up.
Cool.
Yep. I speak for all of my peers, not just those on this call, when I say, yeah, we would love to do that. Anytime you want us to come and give a talk to any of your classes, give us a call.
Cool,
your
thanks.
students are the future leaders of the cloud industry tomorrow, and we want the best leaders we can get.
And with this positive note, YY, John, Dave, and Jim, thank you very much for this insightful conversation, and I hope the audience found it as insightful as I did. Thank you very much all for participating in this panel.
Thanks.
Right.
Take care.
What an amazing panel session, and thank you to all the participants in that panel. What an amazing set of topics discussed, and the deep insight that we've just heard from them is just fantastic. And with that, it actually brings us sort of to the end of this summit track. I want to first of all thank all of you for spending the time listening and being with us and participating in this track with Inside the Research Summit. I want to thank each of our speakers. They've put a lot of effort in, and they've thought a lot about what they're talking about, and they've made it extremely interesting and exciting. Thank you. I think as we went through the track, we've heard about AIM, a new analog optical computer, a new way of solving these hard optimization problems, which I'm sure you'll all agree with me, sounds extremely interesting. We heard about space and about pushing from our planet out and taking Azure from being on this planet to being in space as well. Thinking what we can do with satellites, how we can build services for these satellites, it's been fascinating. We've heard about Project Silica and an update. Project that we've seen go from that ferment phase where we're trying to understand what the technology could be into that takeoff where it starts to make sense. And it's really exciting to see how it's coming together as a real storage system. We then heard about AI Ops, and that sort of challenge of just how do we make the cloud more efficient, more reliable, more controllable, easier to operate, more manageable, and how AI is going to change the way in which we do it. And then of course there was that panel, which again, thank you to all the participants, it was great. Now for all those researchers doing and thinking about the cloud, I just sense that now is an opportunity. In fact, more than opportunity, we have a responsibility to think about the future. So much of the technology and so much of what we do is beginning to get to the end of its life. We need to think what the future looks like and how we are going to enable it. It's critically important. Over the last 20 or 30 years, we've seen so much progress. And yet looking forward, it is harder to see how that's going to happen without us working more together across many different levels, between hardware and software co-design, thinking of the services, how we make the services more efficient, how we get more performance from the hardware that we have, and how we create the hardware for the future. This is a time of immense opportunity and responsibility. And I'm looking forward to seeing what you all do, as well as what we do in the coming years. So with that, I just want to say thank you again for attending, and I look forward to seeing you again next year.
That's a wrap for Day 2 of Microsoft Research Summit. I hope you've enjoyed another day of presentations and discussions among researchers at Microsoft and our colleagues around the world. We'll reconvene tomorrow for our final plenary session on how research is empowering medical professionals and researchers in the health and life sciences, followed by our final day of tracks and sessions. See you then.